Thank you, and thank you very much to the organizers for the invitation. I'm sorry I'm not able to be there in Leeds, but it is a great joy, nevertheless, to speak today at this conference celebrating work of Kobe Peterzil and Sergei Starchenko. Today I'm going to talk about groups definable in minimal structures, and Kobe and Sergei made a gigantic contribution to the understanding of their properties and the development of the theory. Here are some reference to their work on the subject, not all of it, some of it, and sometimes also in collaboration with other people: Alessandro Berarducci, Margarita Otero, Anand Pillai, Pantelis Eleftheriou, and Udi Ruszowski. I forgot here to include a very important paper with Charlie Steiner that just spoke. I'm sorry, probably I forgot more. I apologize. Now, I will refer to this work continuously today, sometimes even just implicitly, because it is so fundamental that most results rely on it. Oops. So here, there are a couple of ideas that this talk is based on. First one, in mathematics, we often see similar phenomenon in different areas, seemingly unrelated. For instance, for finite groups, we have Sylow's theorem, that is, whenever P divides the cardinality of the group, there are subgroups of order a power of P that we call P groups. P Sylows are maximal P groups, and they are all conjugate. In algebraic groups, it has been noted that Borel subgroups looks like P Sylow in a way. They are maximal connected solvable algebraic subgroups. They are conjugated all as well. And for them, the role of cardinality is played by dimension. In Riemann groups, we have tori that are abelian connected compact subgroups. They are all contained in a maxima, torus, and again, they are all conjugate. Moreover, when the groups have finitely many connected components, then we can also find maximal compact subgroups. Again, they are all conjugate to each other. Now, these three types of subgroups, P Sylow, Borel subgroups, maximal tori, they all appear in groups definable in minimal structures through the minimal Euler characteristic. Using the minimal Euler characteristic, Strebonsky in the mid-90s defines P groups and P Sylows and proves corresponding Sylow theorem. Now, in finite groups, Euler characteristic and cardinality coincide. So for P primes, in finite groups, they are the same object. What about Borel subgroups? For definable groups, Borel subgroups correspond to maximal definable subgroups with Euler characteristic 1 in absolute value. In fact, Kobe and Sergei proved that they are all connected and solvable like Borel subgroups. And one can also show that they are definably cocompact. Now, in algebraic groups, Borel subgroups are cocompact, which means that the quotient as a topological space is compact. In minimal structures, this is also true definably, namely the quotient of the group by these maximal definable subgroups with Euler characteristic 1. We know that it is a definable set by work of Edmundo, and we can also prove that as a definable set, is definably compact, which in a minimal structure means that if the topology is the same induced by the order topology, then it is closed and bounded, like we have over the reals. What about Lie groups? Well, Strebonsky defines also zero groups. And it turns out that this will play the role as tori for Lie groups. So P prime explain usual PC law. P equals 1 explain Borel subgroups. And for P equals 0, with some caveats that I will try to explain, we have tori. This is somehow related to the second idea that maybe groups definable in minimal structures are closer to algebraic groups that we give them credit for. First of all, trivially, finite groups, they are all definable in any minimal structure. Then, if we take an algebraic group over an algebraically closed field of characteristic 0, this group, as an algebraic group, it means that it's the solution set of a system of polynomial equations, and the group operation is polynomial as well. Therefore, if we take any maximal real closed field, we know that if we just add the square root of -1, we get the whole algebraic closure. So any algebraic group is going to be definable in it. So algebraic groups over an algebraically closed field of characteristic 0, they are going to be definable in real closed fields. So given that we have this inclusion, one may ask, if we take an arbitrary definable group over a minimal structure, how close it is to an algebraic group? When the group is definably compact, a lot of work has been done following Pillai's conjecture. We know that there is a canonical compact Lie group, G over G00, that has the same dimension, same homotopy type, same first order theory as G. But in fact, compact Lie groups can always be given a structure of an algebraic group, thanks to a theorem of Chevalley. So we can view all those results as analogy to algebraic groups. This for compact group. So what about non-compact group? Well, here too, for example, if we take groups that are definably simple, Peterzil, Pillai, and Starchenko again proved a strong similarity because they show that these groups can be characterized by being elementally equivalent to a simple Lie group. But again, every simple Lie group is algebraic. So here we have again a huge similarity. So one may ask in general, which groups are elementally equivalent to an algebraic group? Are we able to characterize them? For solvable groups, we have a counterexample. Peterzil, Pillai, and Starchenko again give examples of solvable groups that cannot be elementally equivalent to an algebraic group. But what about nilpotent? For abelian, we know it. They are all elementally equivalent to an algebraic group of the same dimension. What about nilpotent groups? Can we find a nilpotent algebraic group with the same dimension elementary equivalent to an arbitrary nilpotent group definable in a minimal structure? We don't know. And then for algebraic groups, we have the Jordan-Chevalley decomposition. And one can ask, what happens to this decomposition in a minimal structure? The answer seems to be that we can get a corresponding decomposition where the role of the unipotent radical of an algebraic group is played by what here I call NG, which is the maximal normal definable torsion-free subgroup of G. Like the unipotent radical, Ng is contractible, so topologically trivial, but it is not always nilpotent. In general, it is solvable, as Kobe and Sergei proved. So let's start from the beginning. If we take a minimal structure, the main feature is that every definable set can be partitioned into finitely many cells. So cells can be defined inductively in M together with their dimension. So in M, a point is a dimension is a cell of dimension 0, and an open interval is a cell of dimension 1. Then, given a cell in M to the power k, in M to the power k plus 1, the graph of a continuous definable function on C will be a cell with the same dimension. And if we take the region between two of those functions, we get a cell of dimension n plus 1. Now, partition is not unique in cell, but as Lau and Dendry proved in his book, there are two very important invariants: the dimension, that can be defined as the maximal dimension of the cell in any cell decomposition, and the Euler characteristic, which can be defined as the sum of the even dimension, the number of even dimensional cells, minus the number of odd dimensional cells. And Lau gives a very enlightening example to introduce the concept, which is if we take an open interval, any cell decomposition will have k points and k plus 1 intervals around them. So giving Euler characteristic -1 all the time. Now, actually, these two invariants, if we are in a minimal expansion of a field, these two invariants characterize sets that are in definable bijection. And so here we have a couple of properties of the Euler characteristic. So for finite set, it's going to be corresponding to the cardinality of the set. And the second property, the multiplicative property, implies that if we take a definable subgroup in any definable group, then the Euler characteristic of the group is going to be the product of the Euler characteristic of the subgroup times the Euler characteristic of the set of cosets of the subgroup. So here we have Cauchy theorem for definable groups. So if we have a group and we know that the Euler characteristic is a multiple of P, then we can find the elements of order P. For the proof, we take the set of elements A1, AP in G to the power P, such that the product is the identity. And this is in definable bijection with the G to the power P minus 1, because the last element is given. Now, for what we have seen before, because we're assuming that the Euler characteristic is a multiple of P, then also the Euler characteristic of any power of G is going to be a multiple of P. And therefore, because the Euler characteristic is invariant by definable bijections, then we have that it's the same for S. Then we have that ZP acts on S by translations. And if we call S0 the fixed point in S, with a little bit of work that here it's not included, Strebowski proves in general that given an action of a P group, then the Euler characteristic of S is going to be equal to the Euler characteristic of the fixed point S0 plus a multiple of P. And therefore, we get here that it is a multiple of P. And so we get elements of order P. Now, thanks to this theorem, then we can characterize torsion-free groups definable in a minimal structure precisely as those groups that have a minimal Euler characteristic equals to 1 in absolute value. And as I was said before, those are solvable and definably connected. And one can prove that they are definably, that every definable group has a maximal torsion-free definable subgroup. So these are the subgroups that before I was referring to be like similar to Borel subgroups in algebraic groups. So those are the torsion-free definable subgroups. So we can find the maximal torsion-free definable subgroups, and the quotient is definably compact. And Kobe and Sergei proved that they are all conjugate. So then Straboski defines P groups for P prime and P equals 0. For P prime, G is a P group if for every proper definable subgroups, the Euler characteristic of the coset, the set of cosets, is a multiple of P, and for 0 if it is precisely 0. Then he calls maximal P subgroups P silo, and he proves corresponding Silo's theorem. So each P subgroup is contained in a P silo, and they are all conjugate. And as it happens for the case of finite groups, once we have a P subgroup of G, we know that it's a P silo every time the Euler characteristic of the quotient, it's not a multiple of P. In the case of 0, it is just different from 0. So, for example, then in the finite case, we have precisely the same notion. So finite P groups are P groups with this definition. So for infinite group, for example, if we take, so this is the group of motions of the plane, we take SO2, which is the unit circle, we make it act on R2 by multiplication. And here for each P silos are gonna be the conjugate of the subgroup isomorphic to SO2. Notice that every 0 group is in particular a P group. So in this case, because the group is definably connected, they all coincide actually with with 0 silos. P silos and 0 silos, they're all the same. Now, to substantiate the claim that I said before, that 0 groups looks like tori for Lie groups, Straboski noticed that 0 groups are abelian and definably connected. What do I mean by definably connected? Well, the fact is that in minimal structures, so we have an order, so we have the topology induced by the order, and then the product topology on the power. But as soon as we have Aleph zero saturation, then closed interval are not connected, not compact. So we need a different notion that capture connectness and compactness. So this is the usual way in which one restricts oneself to definable sets. And the Pillai proves that in definable groups, the definably connected component of the identity, as always, finite index, and it's a normal subgroup. It is the smallest normal subgroup of finite index. So here we have another similarity with algebraic groups, because unlike Lie groups that can have infinitely many connected components, algebraic groups always have finitely many connected components. Moreover, in algebraic groups, one can find always a finite subgroup that meets all connected components. Now, Edmundo proved this in the nilpotent case. It turns out to be true in general. So we distinguish two cases. In the case in which the minimal Euler characteristic is different from 0, this is actually equivalent to say that the definably connected component of the identity is torsion-free. And in this case, we can find a finite subgroups, which is unique up to conjugation, that completes the definably connected component of the identity G0. In the case where the minimal Euler characteristic is 0, we cannot always find a complement of G0, but we can find a finite subgroup F in the normalizer of any 0 silo. So this is another point.
I think we have a question from someone online.
Oh, sorry. Yes.
Oh, okay.
Do you hear?
Easier. Cool. Thank you. Yeah, my mistake. You can continue.
Sure. Please interrupt me anytime. So then this is another point of similarity then with the algebraic group. But I have to say that also for Lie groups, actually, when the Lie group has a finitely many connected components, then one can find a finite subgroup that meets all of them. Now, a key ingredient for to show this is the Frattini argument that it's well known for finite group. There's also a version of it for compact Lie groups for algebraic groups that often it is formulated in terms of actions. But in any case, the point is that when we have a normal subgroup, if we take a P silo of this subgroup, then the normalizer of this P silo completes the group. So the product of the normalizer and H is the whole group. The proof is basically the same in all these cases. And it goes that one, of course, looks at the conjugation map, that it's a definable automorphism of H. So the conjugate of S is going to be another P silo of H, because the Euler characteristic is invariant by definable bijection. And because P silos are all conjugate, then we can find an X in H such that these two are the same conjugate. And therefore, GX inverse is going to be in the normalizer. And then this generic element G can be written as a product in this way. So then here we have these results that gives us a nice finite subgroup for a disconnected group in analogy to algebraic group. So here on the point of torus, I mentioned at the beginning that like 0 groups, they are going to be like torus. One needs to be careful about the 3 different categories that we have. Every time we have an algebraic group, we have 3 groups. For instance, if we take the multiplicative group of the complex number, this is a connected algebraic group, and it is the one-dimensional algebraic torus. So algebraic torus, we can define them to be power of this group. Every time we have an algebraic group, we have the corresponding semi-algebraic group, as we said before. Now, this becomes 2-dimensional over the reals, and it's the product. It's going to have a piece, which is going to be torsion-free, contractible, one-dimensional, and it's going to be another piece, which is going to be a torus, a circle. It's going to be compact. And it's going to be a definable torus because it's abelian, definably connected, and definably compact. Here, it's how we defined definable torus. As a really group, then it is a product of the one-dimensional. It's going to be a contractible group and a torus, abelian connected compact. Now, I think that the fact that when we move from the complex number to the reals, we have this difference that the one-dimensional algebraic torus becomes divided in two parts, one which is contractible and the other one which is compact. It is what explains the fact that zero groups may be not compact. So in this sense, they are different from torus. In really groups, tori are always compact, while zero group may be not compact. So here it's the example that Strebowski gives. This is a semi-algebraic groups where it is a zero groups. The only definable subgroups are the one-dimensional torsion-free subgroups corresponding to the reals, and then there is the torsion. But this is actually like the group above. It's just that the circle, it's not definable because here it's given by the exponential function. So it is not the semi-algebraic. But this is, in fact, is the same group as above, as an abstract group. Okay, so now, keeping in mind these distinctions, between algebraic torus and definable torus, what happens to the Jordan-Chevalley decomposition? I mentioned at the beginning that we get more or less the same thing, except that the role of the unipotent radical is played by NG. This subgroup NG, I introduced it in my PhD thesis while I was looking at the homotopy type of definable groups, but actually I refer to a work with Anand Pillai because it's there where it is proved that it exists, and we used it there for other things. For instance, we use it to characterize definably amenable groups. Okay, so sorry, it's really hot here. In linear algebra, we learn the Jordan canonical form, right? So if we take an invertible matrix, let's take it invertible. If we take an invertible matrix over the complex number, then it is conjugate, or we say similar, to a matrix that we divided in Jordan blocks, right? But these Jordan blocks, we can divide it in two pieces. One piece with the eigenvalues, so the diagonal, and the other piece with the unipotent matrices, so the Jordan blocks with ones of the diagonals. So we have this decomposition, so every matrix can be decomposed into this product this way, a part which is diagonalizable, and the part which is unipotent. Now, if we start with an algebraic group, the cool thing is that the factors of this decomposition belong to the group themselves. And then one can consider all the pieces given by the unipotent parts, and they form a subgroup, which is normal, which is the unipotent radical. And then we can consider all the pieces which are diagonalizable, and these also form a reductive group. Now, what the Jordan-Chevalley decomposition says is precisely this, that the unipotent radical is a semi-direct factor, and then also, and that the reductive group can be decomposed. It is a central extension of a semi-simple group, where semi-simple means that there are not abelian normal connected subgroup, and coincided with its derived subgroup by an algebraic torus. And also the reductive subgroup K is unique up to conjugation. Now, what happens in a minimal structure? Well, we have precisely the same decomposition. If we start with a group that is linear, where by linear, I mean that there is a definable injection of G into GLN R for some real closed field. So let's take it connected for starting. Then we find that NG from before, the largest normal definable torsion-free subgroup, is a semi-direct factor definably. We can find a definable complement, which is going to be, again, a central extension of a semi-simple group by a definable torus. And it's going to be unique up to conjugation. Now, the difference is that NG, it's not always nilpotent. And as I said before, I think that the point is that in the linear algebraic case, we have an extension with an algebraic torus, which has a contractible part and a compact part. So when we move over the real closed field, what happens is that the contractible part of the algebraic torus, it's going to get into NG. And it's going to be the part that it's going to make possibly NG not nilpotent. And then the rest is basically the same. So the main part of the proof are here. We start with a Levy decomposition of G, found by Petr, Zilpila, Starchenko, that every linear group has. So R is going to be the solvable radical, which is the maximal normal solvable definably connected subgroup of G. And S, it's going to be a Levy subgroup, a maximal definably connected semi-simple group, which means that it's not going to be definable abelian infinite subgroups. The first step is to show that every zero silo of the normalizer of S, it's also a zero silo of G. So remember from before, we said that every time we have a zero group, to find out if it's a zero silo, we just need to check that the Euler characteristic of the quotient is not zero. So here, the idea of this step is that we know that torsion-free groups have Euler characteristic 1. So the idea is try to reduce to torsion-free group. And the way one can do it is to look at the normalizer of S in N, which is torsion-free. And then one can prove that there is a bijection between the cosets of the normalizer in G with the cosets of the normalizer in N. And because there is this definable bijection, we know that the Euler characteristic is going to be 1. And so then with a couple of steps, we can then show that the Euler characteristic of G over A, it's different from 0, it's 1. And so we get this first step. Then as a second step, we can find a definable torus in A that such that the solvable radical R is the semi-direct product of NG and T. So essentially, we find a definable torus that completes NG in the solvable radical. So here, the idea is that we looked at the normalizer of S, so that every time we have something in it, we know that we have a subgroup, right? So here, in this case, first of all, we look at the intersection between A and the solvable radical, and we can prove that this intersection is a CELO of the solvable radical as well. And therefore, we can find a part of it that a definable torus that it's gonna complete NG. And then finally, we can prove that this T centralizes S, so that when we take the product between T and S, we get a subgroup K that completes NG in G, because we get everything, right? The T completes NG in the solvable radical, and then we have everything. And the reason why T centralizes S is that we can prove that T is the smallest subgroup containing the torsion of T. And because T is going to be normal in TS, we know that TS is going to be a subgroup because T is in the normalizer. That's why we started with the normalizer, so that the TS was supposed to be a subgroup. And then the torsion, if we fix the K, the K torsion subgroup, then it's going to be a normal subgroup of T, which is normal, and therefore it's going to be central. But then because T is the smallest definable subgroup that contains the torsion, then T, it's going to be central as well. And therefore in TS, it's going to be central in TS, and therefore centralizes S. And so we have this decomposition, which is very similar to the Jordan-Chevalier decomposition. At this point, one may ask, okay, you get that, but maybe one can find something better. Maybe one can find really an important subgroup of NG, which is a semi-direct factor, so getting something similar to the Jordan-Chevalier decomposition. I cannot claim that there's not something better than this. What I can claim is that I tried all the usual suspects. So there are at least 4 nilpotent subgroups that one think of here. One is, of course, first of all, the maximal nilpotent subgroup in NG, so the nilpotent radical. This subgroup does not work because one can find, just as an abstract group level, it does not always split. So one can find example of super solvable Lie algebras over the reals where the nilpotent radical does not split. So that it's hopeless. But then there are more subgroups one can look at least the ones I know. One can look at the unipotent radical in the linear case. One can look at the commutator subgroup of N, and one can look at the commutator subgroup of R. These will all be nilpotent and will always be definable because of theorem of Baron, Jallikot, and Otero. In the solvable case, the commutator subgroup is always definable. Now, this is an example that shows that these 3 subgroups do not work in general. So here we have N. Here is the subgroup of 5 of dimension 5 of matrices 5 by 5 that you see on the left. This is nilpotent. We can make SL2 act on it. This is just the usual action of a matrix multiplication of SL2, but is done through the exponential function. So that if we take, so this is a group definable in Rx. so by a theorem of Wilkie, is an amenable structure. So it's an example. And the unipotent radical here is going to be the subgroup where A and B are 1. And if we quotient by that, we have a non-trivial action of SL2. So it's not a central extension. If we take the commutator subgroup of N, this is it's gonna be even smaller. This corresponds to the subgroup where X and Z are 0. So it's one-dimensional. It's just isomorphic to R. It's the center of the Heisenberg group up there. So it's not going to work as well, because again, we have the trivial action of SL2, and so it's not a central extension of a semi-simple group. Here, the solvable radical coincides with the N, so in general, it's not going to work, the commutator subgroup of the solvable radical. So these are the groups that I know that are nilpotent, that one can find canonically. And so I think that this may be the best analog of the Jordan-Chevalier decomposition one can find in amenable structures. Now, what happens in general?
Sorry, we have a question.
Yes, yes.
Is this a linear group?
Is this a linear group?
Pardon, I couldn't.
Is this a linear group?
This one?
3.
3, 2.
Yes. Yes. I think so.
Okay.
Yes, because it's already in the right form. So if we take any semi, isn't that any extension of, so this is a semi-direct product of two linear groups. I think every semi-direct product of two linear groups is where the action is, I think so. How can it be linear? What?
We're just getting a microphone to the person who's asking questions.
Okay, maybe I'm wrong. Just because the action, I thought, is given through the exponential, so maybe, but maybe I'm wrong.
Right. So I will have to double check, but in my mind, so because I have in mind a theorem about the linear groups that is in some form, and it's on this form. But the thing I don't remember if it's also the other, you know, if it's if and only if. But I will have to check. But my guess it's yes. My guess it's yes. But yeah, but it's a good question. So what happens in the general case if the group is not linear? So here it's an example of a group where the NG does not have a complement, so it's not a semi-direct factor. So here we take, there is a semi-algebraic Tuco cycle that defines the universal cover of SL2. So one can define the group operation on Z times SL2 such that that it's just given by a semi-algebraic Tuco cycles with the values -1, 0, 1, and here you have the group operation. So if instead of having this group over Z, we just extend it to the reals with the same operation, because the cocycle is semi-algebraic, this is just like that. So we get a semi-algebraic group. And in this case, we have a trivial intersection between ng and s, which is given by the integers. And so we do not have we don't have a complement at all, no, even abstractly, because if we could find the complement of an ng, essentially we would find SL2 inside the universal cover of SL2, which is not possible. So in general, then we have a decomposition of G in NTS. So this looks like before, right? Where T was a torus centralizing S, but here definability changes. So N is definable, but everything else maybe not. So S maybe not definable, T maybe not definable, and S maybe not. So all the various subgroups you can build here maybe not definable. So this decomposition then has an immediate application to the commutator subgroup. If we look at this example 2, the commutator subgroup is universal cover of SL2, right? Because the universal cover of SL2 is perfect, and we have a central extension of it. So that's going to be the commutator subgroup, which is not going to be definable. So then we have cases where we know the commutator subgroup is definable. As I was mentioning before, Barrow, Jaligot, and Otero proved it for solvable groups. Then Barrow also proved it for linear groups and simply connected groups. And in general, here the decomposition from before helps us understanding how it looks like, because that torus T that centralizes S can be ignored. So in the end, the commutator subgroup is going to be the commutators of N and G, which is going to be definable torsion-free, and then S, a Levy subgroup of S. And the definability of this commutator, so the smallest definable subgroup containing it, it's going to depend on that intersection we discussed before between Levy subgroup and the center. So the smallest definable subgroup is going to be the smallest definable subgroup containing that intersection times the commutator subgroup. And then as a corollary, we get that then if G has definable Levy subgroup, then the commutator subgroup is always definable, and the definably connected component is this one. Now, I believed for a long time that the two things were equivalent, and finally I found a counterexample. So the other implication does not work. We can build groups where the Levy subgroups are not definable, but the commutator subgroup is definable. So the other implication does not work. So I see that I'm out of time, so well, I will skip this. Lot of stuff. So I'm just saying that all the boxes that I had along the way, they were all part of a recent preprint that you can find on arXiv and on my webpage. Then if you are new to the subject, it may be overwhelming because there is so much literature on that. So these are the 3 surveys that could be a good start, and you can find them all on our web pages. Thanks.